Hi, Irit. Thank you for joining us to do the video polylogue for the Simons Institute. It's great to have you here. I'd like to start off by asking you, what inspired you to become a computer scientist?
Okay. Hi, Lakshmi, and thank you for having me. What inspired me to become a computer scientist? I guess I chose to major in computer science, kind of for silly reasons. I was really into math, and I was sure I'm going to study math, but computer science looked like a good profession, and it was much harder to get into computer science, and I had very good grades, so I thought, it's worth it to do that as well. But I really loved it when I did my undergrad, and then when I finished, I went. The last course I took was a course on complexity, and I really loved it. And I went to the professor who was teaching this, and I told him, I love this area, and maybe I can work on this area. And he told me, this area is kind of dry and there's not much to do, so I would recommend that you come and work with me on something I'm not gonna reveal. So I was quite disappointed, and but then he saw that I'm disappointed. He told me, you know what? There's some new faculty member coming next year, and he's working on PCPs. Why don't you go talk to him? And that's what I did, and I ended up working with Muli Safra, which was great. And yeah, and then I really loved this connection between working on, something that has to do with understanding proofs and why they're resilient and how to randomly check them. These are objects that are both mathematical, and the research is very rigorous, but on the other hand, there's something philosophical about these objects and what it is that randomness gives you, and what does it mean to be local or global. So I really love this merge of philosophy and math, and I thought I found it in TCS.
Okay, great. So when everyone thinks about computer science, they're usually thinking about the world's fastest computer or the best computer in the world, and no one actually thinks about the theoretical aspects of computer science. So if you were talking to a layperson or even a scientist who's not in your discipline, not in theoretical computer science, how would you position what you do based on what they know? Rather, how would you describe your work?
Yeah, that's a question I struggle with. Even though I've had so many years of attempts to explain what I do, I find that I struggle with it often. If it's another scientist, it's a bit easier, because then I don't feel I need to explain what scientists do, which, we want to understand something just for the sake of understanding it. At least this part is kind of obvious. So then I can speak straight to the topic, which is, I study certain mathematical objects that have to do with really the core of computation. And often people don't understand what you mean by that. So then I'll kind of zoom out and say, it's in the intersection of two fields. One is computer science and one is mathematics. And while computer science has to do with things, like in the industry, Google or whatever, and mathematics, they also think that they know. I try to explain the connection between the two, that you really study things like mathematicians, understanding them fundamentally, but you're also connected to, computation and things that happen in the world of computation. And I also sometimes talk about timescales, like that, why do people even pay me to do what I do? Why do governments fund theoreticians, right? And people often are puzzled about that, like why do governments fund us? And then I say that history has shown that even if you study math just for its own beauty, often consequences have a lot of applications. So it's worthwhile to invest in that, and that in our field it's somewhere in between. We study things for their own beauty, but decades down the line, they have amazing consequences. And so, there's a spectrum of how close you are to practice versus completely basic science, and that this field is somewhere in between, something like that. Yeah.
What advancements were most surprising or startling, and how have they shaped your own career trajectory?
Yeah. So one thing that was very pivotal, I guess, for me was in around 2015, I was feeling exhausted from the things I was doing up until then. And I started looking around at different areas. I looking at biology, evolution, and other things. And then I learned about this thing called high-dimensional expanders. There was a seminar run by Tali Kaufman and a mathematician, Bernstein. And at first I just came out of curiosity, and these are very strange mathematical objects that I had no sense what they are. And then at some point they managed to convey something about these objects that I realized this is what we are looking for in this area of PCPs. And I was like, pfft. And then, you know, this field, high-dimensional expanders, is very mathematical and very far from the things I know. So it was needed a lot of motivation to get into it. But once I got that hint, I was like, yeah, I'm gonna invest everything into this. And for me, this was a completely pivoting moment for my career. And you know, I'm really enjoying it. It caused me to learn a lot of pure mathematics. Luckily, the way that worked out for me was just to collaborate with a lot of people and talk to them and learn from them. For me, this was much better than reading books. And you know, maybe it's because I'm more lazy, but it's just easier to talk to people. And yeah, so it's really given me a new world in which to do this research that's both different and informing to this same old area. I guess some things that started out one way, you know, blew up and became something else, and that's something that you don't expect, and it's very kind of, I don't know, exciting. For example, one example that I had firsthand, I don't know, participation in is this area of privacy. When I was a postdoc, I was hanging out with a fellow postdoc, Kobi Nissim, and both of us kind of were talking about the notion of privacy and trying to understand if this is something you can study as a theoretician. And we were kicking around ideas back and forth and talking about it. And we ended up writing a paper on privacy of statistical databases. And for both of us, the feeling was that this kind of research project is very experimental, in the sense, not that we did experiments, in the sense that it had nothing to do with things I was familiar with the kind of research I knew. And it was very kind of a bit esoteric, maybe I would say. But then, you know, this area took off. Kobe continued. I already had nothing to do with it, but the field really took off. And then they wrote the differential privacy paper, and became a whole area. I think it's also very impactful on real life. I hear that industry companies actually implement these things. So for me, this was quite an exciting thing to watch from the sideline, but also, you know, I was there at some initial starting point. That's very nice. Of course, something like that is also going on with PCPs, which is my more mainstream area that I've been involved in since I was a grad student, where when I was a grad student, we didn't think that PCPs are ever going to be practical. I remember one of my family members asking me, you know, can you implement it? And I burst out laughing. But these days they're implemented, you know, and there are companies that are doing these things. And there's more, you know, the list goes on. There's other things like zero knowledge and so on that was completely theoretical and now has gotten a life of its own. So I don't know, I find this whole trajectory from basic science to practice kind of incredible.
Right. And can we talk about some of the applications, potential applications for the high dimensional expanders?
Yeah, well, we don't know, right? High-dimensional expanders come from number theory and other pure math. So far, we've managed to use them for various things. I'm not talking about my own work necessarily, the community that works here. You know, they're good for certain random walks converging, there are certain error correcting codes that are built using them. Maybe one day we can build PCPs out of them. And these kinds of objects, codes and PCPs, will certainly have the potential of being applicable, although one never knows, right? It's hard to predict.
So Irit, as a researcher and as a mentor, you and your research group have contributed so much to the field. And would you like to comment on what you believe would be like some of your most important contributions?
Yeah, I guess it's a kind of question that you sometimes hesitate to answer, right? Because you don't want to admit to yourself that your important contribution is in the past and not in the future. But okay, anyway. I guess for me, I had this proof of the PCP theorem by gap amplification. Back then, this was like 2005 or 2006. There was this thing, the PCP theorem, which tells you how to encode computation in a way that makes it resilient to noise or to errors, even adversarial.
Mhm.
And this was like a very impressive theorem. And when I learned it, the construction and kind of the way you prove it was very complicated. Now, now that I say it, today we don't think of it as so complicated. But back then it seemed very composed of various different parts. We didn't understand the role of different parts, and it was mysterious. And this proof was more, I don't know, combinatorial or simple to me at least. And I was very happy with it that I could find a completely different proof for the same theorem that gave a different explanation of this theorem. And, it also much easier to teach. Like the earlier PCP theorem, you needed probably 8 or 9 lectures to teach it. And this one was kind of more easy to convey to others. So maybe that was a nice thing. And it's also very nice that even though I reproved the theorem, it was already known, so you can say it's not, so important, but somehow the community really received it well, and kind of I got the feeling that people appreciate the fact that you find a different, maybe simpler proof for something, and yeah. And maybe I can also mention that this proof was using expanders to somehow propagate the errors and make the thing more robust. And it combines well with my current research. I kind of view my current research as some kind of an extension of that. So in that sense, I feel that I'm now studying expanders in higher dimension. And these give maybe new lens to view the same proof in a bigger or a broader framework. I don't know.
Okay. So looking ahead, what do you think are some of the most fascinating questions in theoretical computer science, and where do you think the next challenge or challenges lie?
Yeah, it's hard to be a prophet. I can say okay, I can say this. I think that this area of TCS, theoretical computer science, one of its beautiful strengths is that it has the freedom to look around at the world and see, different phenomena and, computational or interaction or whatnot, and to just, model them and study them and try to reason about them, come up with algorithms. And it keeps the area very lively and very kind of very modern. Like it's always looking at what's going on right now. And it's always finding very interesting questions and models. And at the same time, it has the depth and the tools to analyze these things in a very interesting and not a superficial way. So I think the interesting challenges will continue to be along these fronts. If I've mentioned the area of differential privacy, sorry about that. There's this area of algorithmic fairness, a lot of questions that come about because of the importance of computation in our everyday lives, that TCS has something to say about them. Now we have large language models that give a lot of new challenges of, how to use them and also how to abuse them or to prevent their being abused. And this raises a whole new area of questions and models that I'm sure people will study and so on. So I feel that's one big direction that is very interesting. Of course, there are many others. There's this whole area of sublinear algorithms and property testing and streaming, where you understand that the input is huge and maybe your algorithm only looks at small parts of it, and you still want to make reasonable computation. So, all our classical algorithms that looked at the entire input now need to be revisited from this new lens. Yeah, and quantum computation is an exploding area, and there's many beautiful directions.
Okay, great. Regarding gender disparity in computer science, there was this New York Times article which came out maybe a few years ago regarding this paper, which talks about 27% of computer science researchers are women, and the realistic, or rather the most realistic possibility of achieving gender parity is more than a century later. So compared to when you became a computer scientist, so do you believe the computer science field has improved in terms of increasing gender diversity? And in your opinion, what more needs to be done to tackle gender disparity, particularly in computer science? And if you wish, you could comment on STEM fields in general.
Yeah. Yeah, so certainly gender disparity exists, but I think the situation is better than it was when I was a younger student. Although I'm not sure that the way to measure it is by counting percentages of certain things. Yeah, I'm not sure about that. And also, it's from my personal perspective, I see the fraction of students is not that much different, but I do feel that the atmosphere, even outside our field, just the general atmosphere is much better, I think. One issue is that the issue is on the table. We talk about it. We talk about gender equality. We talk about, having more women in the room, right? When you go to a classroom or to a seminar or to a faculty meeting, usually there's rarely more than one or two other women in the room. So, it's much nicer when it's more diverse. So I feel that just the fact that we keep talking about it, and everyone is aware of it, the men as well as the women, it makes a different feeling. It feels that the community is quite welcoming. We've had some experience with speaking out against sexual harassment. So you feel maybe as a young student or faculty that the community has your back. They won't allow you to experience some difficult things without protecting you, I hope. And so I feel in that respect, things are better. Of course, there's a way to go. And, you say 27%, and it will take so many years for this to improve. I mean, these things don't improve in a monotonic way. It will probably be some kind of leap. So I feel like, maybe we feel like it's all the same, but really something not quantitative is changing, and women feel that they're more entitled to participate. Everyone feels that, maybe even. And at some point it will show itself. This is how I feel. And maybe I'm too optimistic. But yeah, but I'm optimistic. I don't know.
That's good. I don't have anything else at the moment. Is there anything else that you'd like to add about your research that I haven't asked, or the TCS field in general? Any last parting thoughts?
Parting thoughts about the TCS field in general. Yeah, maybe I just wanted to say that I feel like the TCS field is the way that it's positioned between CS and math is really nice, and it's really powerful because we get to, have all this interaction with math, and I feel that the respect for the field from the math community has grown a lot over the years. I feel that questions on computation impact mathematicians in the way they think, in the questions that they care about, and of course we gain a lot from them by, just from their knowledge and hundreds of years of knowledge. And I feel that our field is matured in that sense, that people working in our field now have a much stronger toolkit than they used to have. And I also feel that, when I was a graduate student and I started to go to conferences, there was a lot of talk. I don't know, people maybe have forgotten about this, but there was a lot of talk against doing basic theoretical computer science, and that we should be more practical and, be more close to the industry. And I'm glad that this has subsided and people are now more, well, the field matured. People are more comfortable in doing more mathy stuff. And at the same time, we have some, I don't know, there are some actual success stories that show that this is a good way to go. It doesn't cause your area to completely detach and go off in some random direction, but actually, this is a very beneficial interaction. So I feel like this is a very, very strong point for the field. Probably also the existence of the Simons Institute is a very important driver for this for the field to continue to be strong and grow. And okay, it's a great thing.
Okay, great. Thanks so much, Irit, for doing this. I really enjoyed chatting with you.
Okay, thank you.